Welcome back everybody to our course on memory device technology for AI/ML computing. I'm your instructor Dr. Shubhadeep from IIT Hyderabad. Let's have a brief recap of what we were studying in the last class. So we looked at the several physical mechanisms that occur in both valence change and conductive bridge RRAMs. For VC RAMs, we saw how the creation of the filament happens in the forming step or the set cycle as oxygen ions are kind of ripped away from the metal oxide, which forms the conductive filament. This conductive filament is comprised of substoichiometric oxide. This forming process is controlled through the application of a compliance current. In the annihilation process, it was either guided by electrochemical process, which involved the refilling of these vacancies by applying an opposite electric field. So if set or forming was positive on the top electrode, reset involved applying a negative bias on the top electrode. Or you could also have the thermochemical process where localized Joule heating kind of grabs away or leaches oxygen from neighboring regions, thus rupturing this conductive filament. For CB-RAMs, we saw how by the process of ionization and then diffusion of atoms or rather cations from the top active electrode, you were able to create a filament which constituted of these active metal ions, and by applying an opposite bias you can reverse this process and also rupture the filament. With this, we will conclude our study on the fundamental aspects of RRAM behavior, and in today's class we proceed to look at the performance metrics of RRAMs along with the commercialization efforts in RRAM memory. Okay, so let us begin. The first RRAM performance metric that we would like to review is that of uniformity or variability. As you know, to have reasonably scalable technology, we have to ensure that there is high level of uniformity or low variability in our memory technology. So RRAMs, like most other devices, see two kinds of variability. One is called your device to device variability. So device to device variability is the variability which is seen amongst devices in the same manufacturing process or even in the same chip. And this happens because of there are variations and defects which are spatially different, which is introduced during the manufacturing step. The next is something called C2C or cycle to cycle variability. This indicates the variability that occurs when the same device is switched across different cycles. And C2C variability generally happens because there is a inherent stochasticity in the filament formation and dissolution process. And this is what we will look at in a little bit of detail. So in this particular image, you see that for 100 cycles, the RRAM's IV characteristics have been demonstrated. These gray lines indicate the spread in the IV characteristics across different cycles. As we have been seeing in our course, variability is also indicated by looking at the cumulative probability percentage. And as you can see, the cumulative probability percentage graph for HRS is much more spread out compared to that of LRS. So a natural question which comes to our mind is, this is the case for most RRAM devices, that the variability in high resistance state is generally much larger than that compared to the low resistance state. So a question is, why is that the case? This is because the physical mechanisms involved in the HRS and LRS and their associated variability is also very different. For LRS, what causes variability from cycle to cycle is the number and the size of the filaments can be different from one cycle to the other. So since in low resistance state, it is more like ohmic conduction, even if the number of size changes by few percentages here and there, it will not result in lot of change in the cycle to cycle behavior. However, in the HRS state, what determines the variability is this parameter D. So D here, as you can see in our figure, is the distance between the top electrode and the topmost point of your dissolved conductive filament. And the high resistance state is determined by the tunneling of electrons from this tip to the top electrode. And since tunneling current is an exponential function of this particular distance, you can anticipate even a little bit of changes in D will result in large changes in the tunneling current, and therefore we see high amount of variability, because every time there might be small bit of differences in D which will translate into large changes in the high resistance state characteristics. So the next question to ask is, what could be some viable mitigation strategies to control or to improve the variability in these devices? So the first strategy is something that we are familiar with from our study of both NAND flash and PC RAM. This is called program or verify, or ISPP. So these different pulsing schemes significantly help reduce variability also in RRAMs, as has been shown in this particular graph. So one set of RRAMs, this is an MLC RRAM having 4 states, as you can see, 4 states translates to 2 bits. So this 2-bit memory, when you do programming without any verify, you see that there is a large distribution between neighboring states, and the gap between neighboring or subsequent states is also very tiny. However, the same memory, when you do program and verify, please try to recall, was after every small pulse of program, you check whether it has reached its intended resistance value or not, and if it has, then the process is stopped. This really helps in controlling the standard deviation of your resistance states, and thereby having sufficient margin between these resistance states. However, as we have seen even with ISPP, although it helps in reducing variability, it comes at the cost of increased latency. The second strategy which people use to improve the variability in RRAM devices is by playing with the materials composition and also the interface between the oxide or the insulating material and the top electrode. So in this particular example, as you can see, so you had a hafnia based RRAM, and it had quite a large spread both in LRS and HRS, but the moment you started doping or alloying aluminium along with this hafnia, what happens is there is a significant reduction in the variability as evident in the CDF curves. So why was this reduction in variability or tightening of the distribution possible? This is because the moment you start introducing aluminium in hafnia, the barrier to both set and reset reduces significantly. If the barrier to reset is reduced, it is more likely that the distribution of HRS and LRS tightens significantly. This can be understood with a very simple example. Just imagine that you have a jumping barrier, a very high jumping barrier and a low jumping barrier. Now you call 100 people to jump over this barrier. It is more likely that all 100 people will be able to jump through a small barrier as compared to a large barrier. That is why when you reduce barriers for set and reset, the variability in devices generally reduces. However, it does come at the cost of reduced memory window. As you can see, the memory window has shrunk from 10 to the power of 3 to 10 to the power of 2 for exactly the same reasons. Okay, the next thing of RRAM performance metric that we will look at is that of endurance. So we have defined endurance as the number of program erase cycles, or in this context, the number of set reset cycles that a memory device can endure before there is a reduction or total collapse of the memory window. So from my own experience of measuring lot of RRAM devices, I have seen that the most common failure in endurance comes when the device permanently goes to the low resistance state. In fact, the device goes to a state or a resistance value which is even much lower than the LRS state, as you can see in this particular graph. The LRS state is over here, but when the failure occurs, the device goes to a much smaller resistance state. Why does this happen? It's easy to understand. Due to multiple program erase cycles, there is so much electrical stress on the oxide that the quality of the oxide gets compromised, and therefore there is a permanent hard dielectric breakdown. This hard dielectric breakdown results in a permanent filament to form between the top electrode and bottom electrode, which cannot be annihilated. So what could be the mitigation strategy? Mitigation strategy here also could take the form of either having pulse programming or materials engineering, as demonstrated in this figure. By applying smaller amplitude of pulses but large number of pulses, you can reduce the amount of stress that the oxide encounters, thereby increasing the endurance from roughly 10 to the power of 3 to almost 10 to the power of 6. The other method to mitigate endurance problems is by using materials engineering. So generally this involves increasing the band gap of the material under consideration or improving the interface between the top electrode and the oxide film. How this helps is that if you use a larger band gap material, can withstand larger electric fields and therefore are more robust against electrical stress. So the third thing that we will look at is retention. In retention, we check that once a data bit is written inside a non-volatile storage element and we do not disturb it, how long is that data preserved? As you can see from this image, by changing the material from hafnia to alumina, keeping everything else same, the drift in the low resistance state can be curtailed. As you can see in hafnia films, there is a drift in the low resistance state, but when you use the same configuration with alumina, the low resistance state drift is curtailed to a very large extent. Why is this the case? This is because the primary mechanism of drift in resistance with time when the device is in low resistance state is due to the thermal dissolution of filament. Let's recall that in VCRAMs, this spatial distribution of oxygen vacancies was the reason for this conductive filament, and if you allow the filament to stay for elevated temperatures, there is a chance that these filaments may dissolve due to thermal diffusion of oxygen atoms from neighboring regions. Similarly, the drift in HRS is also possible, and drift in HRS is generally happens by the same mechanisms. The ions which are responsible for the broken filament can now start coming and repairing the filament, and there could be a change in the HRS resistance as well. So as we have seen, thermal energy is a main factor which can degrade the retention of RRAM devices, and therefore it is absolutely essential to claim that you have a viable RRAM technology. You need to perform accelerated testing, which we have looked at in detail for other non-volatile memories, having at least 10 years of memory at 85 degrees Celsius. So what could be the mitigation strategies to improve retention? They are primarily focused towards materials engineering. It is a combination of interface engineering and having oxides as the functional layer with much larger thermal stability. As you could even see that since the band gap of alumina is greater than that of hafnia, the filament which is formed in alumina or aluminium oxide is much more stable compared to that which forms in hafnia. Okay. The fourth performance metric that we will look at for RRAMs is that of multi-bit operation. Now, when we were studying memristor, I had alluded to the digital type of memristor and the analog type of memristor. Please try to recall, there we had studied that the gradual IV characteristics that we see in an analog type of memristor is what is responsible for giving us multi-bit characteristics. So I thought for this example, I will take the device which has been fabricated and measured by myself. So this is the paper that you can read, which came out in 2020. I find that this paper is very interesting because for the first time we had shown that you can achieve multiple resistance states in the thinnest possible RRAM. How did we achieve the thinnest possible RRAM? We did that by sandwiching a monolayer of moly sulfide. So moly sulfide is a 2D semiconductor. Two-dimensional materials are these materials which have almost no height. So this moly sulfide had a height of just 0.7 nanometers. And what we saw remarkably is that just if you sandwich this moly sulfide between two gold electrodes, we see beautiful unipolar behavior which is gradual in its reset. And since it is gradual reset, what we can do is we can stop the reset cycle at different stop voltages. What I mean is you can prevent the device from going completely to HRS state. You can stop the device at different reset voltages, thereby gaining access to multiple non-volatile resistance states. And as we had shown in this paper, that we can demonstrate at least 5 states which are separated by 6 orders of magnitude. So you have sufficient noise margin between the states also. So this is a demonstration of the thinnest possible MLC RRAM at that particular time. However, by using binary oxide RRAMs, researchers have been able to show even better performance in terms of trying to pack many more states. And the trick is not to use DC IV sweeps but to use pulsing. So as shown that by applying just 10 nanoseconds of pulsing at 2 volts, you are able to move reliably from very closely spaced states. And as has been shown that you can get almost 100 repeatable states which are not overlapping. So as you can see in this cumulative distribution function, you see 100 such lines which indicates that this device can operate with 100 closely spaced states. And this property of RRAMs, that you can make it behave like almost an analog memory where there is a linear change in resistance which can be accessed by these measurements called potentiation and depression. In potentiation, you apply pulses such that the conductance of your RRAM increases almost linearly with pulses, and you can reset the RRAM by applying pulses of the opposite polarity. Not only that, you can have access to these multiple states repeatably and cyclically. And this is what makes RRAMs very interesting for analog in-memory computing and also for neuromorphic computing, something that we will study in detail at the end of our course. Finally, we will discuss the array level integration and scalability challenges in RRAMs, followed by some commercialization efforts. So, as we had discussed in our first lecture, the filamentary nature of RRAMs renders it something very, very special. The area scalability of RRAMs is much better compared to charge-based memories such as NAND flash. So in NAND flash, when you reduce the area, remember you started facing the few electrons problem, and that created lot of problems in reliability, memory window, so on and so forth. However, in filamentary systems such as RRAMs, what we notice is that as you reduce the cell area, not only you get better reliability and endurance, also your memory window and power requirements come down. Why does this happen? We see better reliability because in a smaller cell area, the chances of defects occurring randomly also reduce, and therefore reliability and endurance also improves. In the case of memory window, as you can see, both the high resistance state and low resistance state increases as we reduce the channel area. This is easy to understand. The high resistance state reduces because resistance is inversely proportional to the area of conduction, and the low resistance state also increases because the number of conductive filaments starts reducing as you scale down the area. As a result, the memory window starts increasing as we reduce the cell area. Also, because the number of filaments that can occur in a small area reduces, the amount of energy or power which is required to set and reset the device also starts shrinking. And that is why there are several examples and demonstrations of sub 10 nanometer feature size RRAMs. However, we run into serious issues when we start doing the array level integration in form of crossbar array implementation. So, one of the key interesting features of RRAMs is not just that you can arbitrarily reduce the area of the cell size and make it comparable to a nanometer size filament, but also you can pack many of these RRAMs in this crossbar array configuration where you have these bit lines and word lines arranged in a crossbar fashion, and at the intersection of a bit line and word line you have a resistive memory element. So the important question to ask is, does the area scalability of 4F squared also maintained in RRAMs when you go to the array level? It turns out that is not the case because of a very serious issue that occurs when we start scaling RRAMs in crossbar arrays. So this serious challenge is known as the problem of sneak paths. Let me try to explain what is this problem of sneak paths with a very simple example. Let us assume that the cell that I would like to read out is the cell which is marked in red, and in order to do so, I need to apply a read voltage across the associated word line and the associated bit line. However, when I apply a voltage across the word line and bit line, it turns out there are other parallel unintended current paths which pass through unselected memory cells in a crossbar array. And this creates lot of problems during read and write operations when the bias is applied to selected cells which leaks through the neighboring cells. So in this particular example itself, let us assume that these cells which I am marking out are in low resistance state. So in addition to the intended readout current which is shown in black color, there will also be an unintended sneak current which will flow through the top word line, enter through the low resistance state into the bottom electrode, then travel back to the top electrode through the second cell which is in low resistance state, and then find its way into the bottom electrode. And these unintended paths or sneak paths become a very big source of errors, especially in multi-bit cells, where sometimes the sneak currents can be more than even the read currents. And this is what prevents the large-scale integration of RRAM cells. So there are a few mitigation strategies. The first mitigation strategy is to do effective array biasing. So let me explain array biasing with this example. Let us assume the cell that I would like to read out is this particular cell. So what I do is, on the word line corresponding to the cell that I would like to read, I apply V, and corresponding bit line I apply 0. However, I do not leave the other cells floating. In all the other unselected word lines and bit lines, I apply a voltage of V by 2 and V by 2. And this divides the cells in the arrays in 3 categories. The first is your selected cell which you intend to read out, across which the potential difference is V. The other are your half selected cells. Half selected cells are the ones which are there on the same word line and bit line as your selected cell. On the half selected cells, the potential difference across them is just half of V, whereas in all other cells, the potential difference is 0. So in all unselected cells, since there is no potential difference, even if it is in low resistance state, there is no chance for sneak currents to pass through. Even in half selected cells, the intensity of sneak currents will reduce quite substantially. And through this technique of having half selected cells and unselected cells, you can mitigate, you cannot completely remove sneak paths, but you can mitigate or you can reduce the impact of sneak paths quite seriously. However, the methodology which is universally used in the integration of RRAMs into large arrays is by adding something called the selector device. The adding of selector device is something we have seen even in PCRAM technology, where the PCRAM was integrated on the drain of a access transistor. This is also what is done in the case of RRAMs, where RRAMs are integrated in 1T, 1R arrays. So how does this help in reducing the sneak paths? This is done because just like in an 1T, 1C DRAM array, only the row which has the word line turned on is active. All other things become inactive. Therefore, the leakage through all other word lines become nullified. However, this involves increasing the area scalability of the 1T, 1R array, and there is a large variation of what happens to the area scalability, and depending on the process, the area scalability can be as good as 6f squared for large technology nodes where the transistor node is very large, or it can even become 80f squared if the transistor technology node is very, very small. Therefore, sneak paths is the key issue which prevents the area scalability or large area integration of RRAM arrays. With this, let us look at few commercialization efforts in RRAM technology. So the first commercialization effort came in 2012 from Panasonic and Toshiba. So this was not an out and out product, but it was a prototype chip which had 64 KB of flash memory in a microcontroller unit which was used primarily for automotive applications. So we know now that the 1T1R array consisted of tantalum oxide based RRAM cells, and this was the first demonstration to show that RRAMs could be a good replacement for embedded memory applications against the NAND flash. So as we can see in this particular table, the power for writing into the RRAM was significantly lower as compared to that of the NAND flash. This is because the operational voltage of RRAMs is also significantly lower. Also, we saw that there is a improvement both in read and write latencies. In 2013, Toshiba and SanDisk demonstrated the first large-scale array, a 32 GB RRAM based on 1D1R. So D stands for diodes. Sometimes the transistor can be replaced with a diode if you ensure that your RRAM is a unipolar device. So sometimes there are advantages of having unipolar devices. This is because a selector device, instead of being a transistor, can also be changed with a diode. A diode will of course take less space and help in area scalability. However, as was the trend with most of the companies, they generally do not disclose what is the composition of their RRAM. Also, it would be very interesting to notice that as you scaled from 64 KB to 32 GB in memory, there was a significant increase in the read and write latency from 40 nanoseconds to almost 40 microseconds, and this becomes quite comparable to your multi-bit NAND flash as well. In 2014, Sony and Micron came together and showed the first demonstration of a chip prototype made entirely from conductive bridge RAMs integrated in 1T1R fashion, which demonstrated a total size of chip of around 16 GB. What was very interesting is that this particular RRAM array was able to achieve an area scalability of 6F squared, and this was done at the 27 nanometer node. Also, what was significant is that the read latency and write latency of 2 and 10 microseconds was a significant improvement from the previous demonstrations of large-scale integration of RRAMs. Next, I want to highlight a very interesting trend which is evident in eNVM space. Technology startups, the first example I would like to give is that of Crossbar. Now, Crossbar started playing in the RRAM space. Crossbar was formed when there was a technology transfer from researchers at the University of Michigan, and they came up with a very bold claim that by having 3D integration of RRAMs, you can go to a chip which is the size of a postage stamp with a capacity of 1 terabytes. It is rumored that the switching element in these kind of RRAM cells is amorphous silicon, thereby even more improving the CMOS scalability. However, this particular promise took several more years to come close to or to even bring to production. Right now, if you go to Crossbar's website, you see that they have scaled down on the promise of having large memory arrays, and they are focusing more in the embedded non-volatile memory space, which is similar to what Panasonic and Toshiba initially promised. Also, another startup success story is coming from Weebit Nano. This was an Israeli startup in association with the French lab CEA-Leti. They had shown CMOS integration at the 45 nanometer node for titanium nitride SiO2 based VC-RAMs, and they too are showing lot of interesting applications for embedded memories. And at least for our RAMs, it seems like your big giants like TSMC and Intel came slightly late to the party. So in 2019, TSMC showed their first work on RRAMs on the 40 nanometer node with a very tiny capacity of 2 MB per macro. So because TSMC can be very secretive of their processes, we don't have an actual confirmation of what is the device that they were using. But my guess, this is my guess, don't hold me to it, is that they were using 1T1R configuration of Hafnia based RRAMs with an layer of titanium and titanium nitride. This is because ITRI, which is a major research institute in Taiwan and closely works with TSMC, had shown way back in 2008 and 2010 these kind of RRAM structures, and we know that there is a very tight integration between TSMC and ITRI. So this can be an educated guess, but we do not know for sure. In the next year itself, Intel also produced their first RRAM, which was integrated with your 22 nanometer FinFET. So the front end of the line was your 22 nanometer FinFET, and at top metal layers, you had integrated your RRAMs. And what was very special about this implementation is that the read latencies were very, very tiny, and also the read voltages and therefore the power consumption was very, very less. This is because these RRAMs were integrated on low power FinFET technology nodes. Intel have disclosed that these RRAMs were also based on tantalum oxide along with a buffer layer between the tantalum oxide and the top electrode. However, despite having very low power requirements, the area scalability of these were not very good, and it was only 78 F squared. So currently what is happening is, in the RRAM space, major companies like TSMC, ST Microelectronics are integrating RRAMs with their smaller and smaller technology transistor nodes. So in 2020, 22 nanometer was, so in 2020, the integration with 22 nanometer node was announced, whereas in 2024, the integration with 6 nanometer node was also announced. However, RRAMs have a very, very rich application space going into the future. The first application space that people are exploring now is RRAMs for hardware security applications, where the inherent stochasticity in the forming and dissolution of the conductive filaments of the RRAM are not prevented, but they are actually utilized for creating effective true random number generators and physically unclonable functions for crypto engines. So I will not discuss more about this because of the limitations of time, but you can go and read this wonderful article that I have linked for you. But more importantly, the future of RRAMs is very, very rich, especially in the context of our course, because the recent most demonstrations of RRAMs, they are not commercialized yet, but even top companies like TSMC are working on it, is using RRAMs for analog in-memory computing or more brain-like neuromorphic computing for dot product engines. And the promise is, by using analog computing, you will be able to drastically reduce the power consumption for running AI/ML algorithms. But this we will discuss in the last part of our course. So stay tuned for that. With this, we close our study of this very beautiful technology called RRAMs, and in the next class we will start looking at magnetic random access memories or MRAMs. Thank you for your attention. See you in the next class.